Now we're going to go through pressure volume graphs. For this, we're going to have pressure on the vertical. Our pressure is going to be in kilopascals. And on our horizontal, we're going to have our volume. This is a way of relating the pressure and volume of a gas that more regularly goes through a cycle. An example of this would be your car engine. So a car engine will go through a cycle of compression, expansion, compression, and then expansion again. This process allows the chemical energy of the fuel to be converted into mechanical energy. However, it's not done directly, it's done through the movement, the expansion of gas, and that cycle of recompressing the cylinder so that more work can be gained from that gas. So we're going to do a simplified example in this situation, but we can relate it to that engine cycle. Our initial point here is just going to be at 400 kilopascals, and we're going to set its volume as being at 2 meters cubed. The final piece of information for this point is its starting temperature. So we're going to say that this starting temperature is going to be at 300 Kelvin. Now a PV graph is there to show the changes in it. So we're going to change the volume of this gas without changing the pressure. So we're going to start at this point and expand it horizontally at a constant pressure to this point over here, where it's going to expand to a volume of 8 meters cubed. As we have a change in the volume, we are also going to have a change in pressure. Remember that our ideal gas law says that PV is equal to nRT. We have a change in the volume, but no change in our pressure. So therefore, on the other side of it, assuming that our container is sealed, that means that our temperature must also change. So we can say that V on T is going to be equal to our nR on P. So our pressure, universal gas constant, and the number of moles remain constant. Or our initial volume and initial temperature is going to be equal to our final volume and our final temperature. We're after the final temperature in this situation, so we're going to say that T2 is going to be equal to our V2 on V1 times by T1. So that means that we're going to have 8 on 2 times by our 300 Kelvin, which is going to come out as being 1200 Kelvin. So I'm going to also put that on my graph over here. We've moved from a point here of 2 meters cubed all the way up to 8 meters cubed. When we're looking at our ideal gas constant, R is equal to 8.314 joules per mole Kelvin. The joules here relates to the idea that PV is equal to our pressure, which is pascals times by our meters cubed. Pascals is equal to newtons per meter squared, which we're multiplying this by meters cubed. So that means that our meters squared here is going to cancel out with our 3 here, and we end up with just being Newton meters, which is equal to joules, which is the amount of work being done. So that means that if we multiply pressure times by volume, we are going to end up with energy. So that means that this large area here, from our 300 down, across, up, like this, if we find the area of this orange cube, we will be able to find the work done by the gas. So because the gas has expanded its volume, it is doing some work. So if we look at this, we don't need to worry about our temperature in this situation. We're just going to be looking at our change in volume. So that means that our work is going to be equal to our pressure times by volume, which is then going to be equal to our 400, so our constant pressure, times by our change in volume. Our change is doing our final minus our initial, so 8 minus 2. So that is going to be 400 times by 6, and this is equal to 2400 kilojoules. Why kilojoules? Well, our vertical axis here is in kilopascals. So that means that when we applied it over here, we used pascals. The difference between pascals and kilopascals is a multiple of 1,000, so therefore we end up with 2,400 kilojoules worth of energy being done by the gas to expand from 2 meters cubed to 8 meters cubed. Now let's go back to our graph. If we take from our final position that we were looking at here, and we take a vertical line straight down to this point down here, we now have no change in our volume, but we have a new pressure of 200 kilopascals. Let's find our temperature in this situation. So for this point here, we are looking at a change in pressure. So our pressure is changing and our temperature must be changing because its volume is not. So I'm going to divide through by temperature. We're going to say that this is equal to nR on V because the ideal gas law says all of these are constant. Our initial pressure and temperature is going to be equal to our final pressure and temperature, which means that we can then solve for our final temperature by saying that T2 is going to be equal to our final pressure on our initial pressure times by the initial temperature. Our initial temperature is actually up here because we are moving down to there. So our initial temperature is 1200 Kelvin. So we end up with our 200 kilopascals divided by our 400 kilopascals times by the 1200 Kelvin, which is just going to be coming out as 600 Kelvin. So that means this point here is going to be at 600 Kelvin. The next thing we can look at is the work done by this movement. However, when we're looking at this segment here, there is no work being done. Work is a measure of force times by displacement. Now, as the volume is remaining constant at the 8 meters cubed, there is no displacement being caused. Even though there is a pressure change, no work is actually being done for the movement from the 1200 Kelvin all the way down to the 600 Kelvin. No work is being done. So let's do some more work. We're going to move across over here from our 600 Kelvin to back to its original volume. We're going back the opposite way now. So we've gone from 600 Kelvin at 8 meters cubed and 200 kilopascals to 200 kilopascals at 2 meters cubed. So we can use this formula again over here. Because we have a change in volume at a constant pressure, we can solve that again. So our T2 is going to be equal to our V2 on V1 times by temperature 1, which is then going to be equal to 2 divided by 8 times by our 600, and that's going to be equal to 150 Kelvin. Now we have another area. So we've got this area here where there is a volume change at a constant pressure. So let's look at this area here. So in this situation, we're going to be looking at the work done of our blue section. So the work is equal to my pressure with a change in volume, which is going to be equal to, well, the pressure is constant, so that's going to be 200 kilopascals times by our change in volume, which is going to be equal to our final minus our initial. So 2 minus 8. So solving this is going to get us minus 1200 kilojoules. The reason why this is minus is we are actually compressing the volume. So we are doing work, the system is doing work to the gas, compressing it. If we go back to our idea of the engine, this is when it's actually expelling its exhaust. It's pushing out the air. So the air pressure remains constant, mainly because it's going to be open to that of the environment. It then pushes it out. So the engine is actually pushing air out. It's using energy to decrease the volume, to remove the exhaust from the engine so that it could then go through and explode and get energy out of the fuel. Finally, we're going to go back up to our top. So because this is a cycle, we're going to go vertically up. There's again no work in this part, mainly because it has no change in the volume, so no displacement, so therefore no work being done. So the final part of this is the amount of work that we're actually getting out of the system. So what is the net work of the system? For this one, we're able to extract 2,400 kilojoules worth of energy. We also had to compress it again by 1200 kilojoules worth of energy. So the net work would be equal to the work that we got out of it, so the 2400 minus the work that was needed to provide to it, so 1200 kilojoules worth of energy, and that's going to be equal to 1200 kilojoules worth of energy. It just so happens that that value corresponds to this area inside of the graph. So if we were to look at this and do that calculation, the work net should be equal to the base times the height of that rectangle. Our height in this situation is going to be 200, mainly because we're going from a height of 200 up to a height of 400 in our pressure. So our height is going to be 200 kilopascals, and our base is going to be our change from 2 meters cubed to 8 meters cubed, vice versa. So that is the total amount of change that is going on. So that is going to be a difference of 6 of our base. 200 times by 6 is going to be equal to our 1200 kilojoules worth of energy received out of our system. So therefore, that area as a difference of that below and the area inside is equal to the net work that we're able to get out of this cycle. This is just a rectangle. You could certainly get other shapes, but this is the basis of a pressure volume graph.